Hello class, welcome to Geometry Lesson 10.1, Arcs and Sectors. So our question for today's lesson is, how are arc length and sector area related to circumference and area of a circle? Our goal today is to find the arc length and sector area of a circle and use them to solve problems. So since we are introducing the circles unit with the first lesson, there's going to be a bunch of vocab. We'll define a bunch of vocab terms, including arc length, central angle, intercepted arc, major minor arcs, radian, and sector and segment of a circle. So let's go ahead and recall some of the circle vocabulary from last unit when we discussed the equations of circles. So then we described a circle as a geometric figure made of points that are all the same distance from a given point. And this given point is referred to as the center, right? And the distance that is the same from each point on the circle to the center is referred to as radius. And the center of a circle is usually given by the coordinates hk. So each point is a certain distance from a given point, which we refer to as the center, and any line segment from the center to any point on the circle is the radius. Now the diameter is the line segment with endpoints on the circle that pass through the center. So it's essentially two radii. So if I have two completely opposite endpoints on the circle, and then there's this line that crosses through the center, that is referred to as the diameter, which we'll refer to as lowercase d. A chord is any line segment with both endpoints on the circle, so a diameter is considered a chord. But you can also have other chords that do not go through the center, for example, this chord here, and that would be referred to as another chord. The diameter, as we mentioned earlier, is the longest chord in a circle. It is referred to as a chord, and it's the longest chord. And we discussed the equation of a circle, which was the standard form, x minus h squared, y minus k squared, and the sum of those equals r squared. All right, so let's go ahead and define the new terms for the unit. The circumference of a circle. Now we know that the circumference of a circle is the distance around the circle. So if I were on the surface of the earth, for instance, right, and we were looking at it at 2D, then we would just travel around, the globe. Let's say I wanted to travel around the globe, and if I travel one whole revolution around the globe and come back to where I started, then that's referred to as one full circumference, okay? And the arc is a portion of that circumference. So instead of, maybe I would want to go from point A, which is city A, to another country located in location B. And that would be traveling the arc. Okay, so arc is a portion of the circumference of a circle. And in this case, you see this angle, which is a portion of that, the total angle of a circle. So in this case, the arc here, one of the arcs is considered to be AB. But I can also travel from A to B and going this way, right? So there's two ways that I could travel from A to B, the longest route or the shortest route. And those are two different arcs there. We'll talk about those in a little bit. Now, an arc can be measured in a couple of ways. You can measure what we call the arc measure, which is a fraction of a whole circle. Remember that a full circle is 360 degrees. Here, this 95 degrees is a fraction of that circle. So this would be considered the arc measure from A to B. So, which is also referred to as the central angle. This is referred to as the central angle. The arc length is another way that we can measure, and it's literally the distance if I were to travel from A to B, as I mentioned earlier. If I were to travel around the Earth from A to B, then that would be my arc length. The central angle of a circle is formed by two radii. So this is a radius, so two plural radii with the vertex at the center of the circle. And that is your central angle, which is the 95 degrees. As we mentioned, the central angle is APB, and the measure of it is 95. And the measure of the arc, and therefore, is also 95 degrees. So the arc length is a fraction of the circumference. So if the radius of the circle were to be, for example, 1 inch, 1 centimeter, 1 mile, whatever the circle, then the circumference would be 6.28. And we get that from the usual circumference formula, which is 2 pi r. We'll discuss that in more detail later. And if you compute 2 pi times the radius, which is 1, you get 6.28. And then the arc length from A to B happens to be 1.66. We'll show you how to calculate that in a little bit, but the point is that the arc length is always a fraction of the whole. All right, so a central angle, we said, creates two intercepted arcs, and these are the two arcs. We have the arc from A to B, and we have the arc from A to B in the other direction. So those are my two intercepted arcs. Now, intercepted arc is the part of a circle that lies between two segments, rays, or lines that intersect the circle. So in this case, my segments here, those are my two segments. So it lies between that. So this is my arc lying between those. And then, for example, AB would be this first arc. ACB would be the longer arc. AB is what we call a minor arc. And that's because it's the shortest distance here from A to B traveling around the circle. The major arc is the longer distance, and so this is called the major arc. Now the minor arc is smaller, and it's smaller than a semicircle, a half circle. Remember that a half circle is 180 degrees. So this is definitely 95 degrees, so it's smaller than 180. Now the major arc is larger than 180 degrees. In this case, to find this major arc, well, we know that a full circle is 360. So this major arc is, the measure of this major arc is 360 minus 95, which is, roughly 265. All right, so that's going to be the major arc, which is greater than 180. So as we mentioned earlier, the measure of the major arc is 360 minus 95, which is 265, which is more than 180. All right, so recap. The measure of an arc is equal to the measure of its corresponding central angle. So as we mentioned, if I wanted to find the measure of arc JM, then I can just use its central angle right here, given in orange. If I wanted to find the measure of JL, then I would just use its central angle there, which is, they're both indicated in blue. So congruent central angles intercept congruent arcs, and congruent arcs are intercepted by congruent central angles. And this makes sense because if they're the same angle, if these are the same angle, then they have the same congruent arc. All right, so there are a couple ways to measure angles. So we said that, we can measure an arc with what we call the arc measure. Now there are a couple ways to measure angles themselves. The usual degrees, which we're comfortable with, and radians. We're going to introduce radians. So let's recall a degree. A degree is 1/360th of a circle. Remember that a circle is full 360 degrees. So if I have 1 degree, then that means I'm literally that much of the circle, 1/360th of the way of the circle. So if this circle is 360 degrees, then I'm literally just a little chunk of that circle, and that would be considered 1 degree. I stacked 360 of these, then I got 1 full circle. Now a radian is equal to the measure of a central angle that intercepts an arc with a length equal to the radius. So I have this angle here, which is referred to as 1 radian, and it is defined as the angle measure in which the radius, this radius here, is actually the same length as this distance here. So these two are actually the same length. And that is referred to as a radian. So if I have 2 radians, so for example here, 2 radians, then that means that the distance, if I were to travel from here to there, that would be equivalent to traveling 2 radii of the Earth, for instance. So if we knew the radius of the Earth and I were to travel around, then so if I were to travel 2 radians of an angle measure, that means I would have traveled the equivalent of 1 diameter of the Earth, or 2 radii of the Earth. Okay, and that's what 2 radians would refer to as. All right, so that's the definition of a radian. Now we know that the circumference of a circle is approximately 6.28 r, because remember that this is 2 pi. Remember the Greek letter pi is approximately 3.1415, dot, dot, dot. So it's approximately 3.14. And so that's how we get 2 times 3.14 is 6.28. So this means that there are 6.28 radians in a full circle. So a full circle is 360. It's also 2 pi radians, or 6.28. In a half circle, there are about 3.14 radians, or pi radians. So again, as we said, in a full circle, if you were to travel here all the way around, that's 2 pi radians. If you were to travel a half circle, that would be half of 2 pi, which is 1 pi, or 3.14 radians. Okay, so pi rad is 180 degrees. How many degrees is 1 rad? 1 radian. Okay, so if we're going back to this example here, how many degrees, how much is that in degrees? So let's calculate that. Well, we know that 1 radian, we know that pi radians is 180 degrees. So we're going to say that there's 180 degrees for every pi radians, right? And then the radians here cancels out, leaving us with degrees as the unit measure. So we have 1 times 180 is 180. We have an invisible 1 here, times pi is equal to pi. So 1 radian is 180 over pi degrees. And we know that pi is about 3.14. So we do 180 divided by about 3.14, and we get about 57.3 degrees. So 1 radian is the equivalent of 57.3 degrees, approximately. All right, so let's go ahead and practice that, converting from radians to degrees or vice versa. So if we want to calculate 5 radians and we went in terms of degrees, how many degrees is that? Well, as we mentioned earlier, we know that 5 rads is equivalent, so we know that pi rads is equivalent to 180 degrees. So we put rads on the bottom because we wanted to cancel with the rads on top. All right, so we have 180 degrees now. So we have 5 times 180 divided by pi. So we're going to calculate that, 5 times 180, and then divided by pi. So let's do that on the calculator real quick. So 5 times 180 is 900. We have 900 over pi, and we know that pi is about 3.14. So we'll go ahead and do that. We get approximately 286.6 degrees. All right, and that's how many degrees. So it's not quite 1 full circle. So pi over 3 rads. Now we want to go from rads to degrees like we did earlier. So again, we're going to multiply by 180 over pi. Now, just to point this out, you can also multiply by 360 over 2 pi. Because remember, in a full circle, 360, that's also equivalent to 2 pi. I choose to just do, so you could also multiply by 2 pi. But remember that 360 divided by 2 is 180. So this is really the same thing as that. Okay, so I'm using the simplified form. All right, so now we got pi's cancel. Notice that the pi's cancel here, which is nice. The rads cancel as well. So we're left with 180 divided by 3. And 180 divided by 3 is 60 degrees. Now we're going backwards. We're going from degrees to radians. So in order to do this, instead of multiplying by 180 degrees on the top, we're going to have 180 degrees on the bottom because we want degrees to cancel. Remember, when you have something on top, something on bottom, they cancel. So we got 180 degrees on top, and then pi radians, or on the bottom, and then pi radians on the top. So now we got 90 times pi over 180, because there's an invisible 1 here. All right, and then we can reduce this, divide by 90 top and bottom, and it's going to be pi over 2. So 90 degrees is equivalent to pi over 2 radians. All right, 270 degrees, we'll multiply by 180 on the bottom so that the degrees cancel, and pi on the top. So we got 270 pi over 180. We can divide top and bottom by 90, leaving us with 3 pi over 2 radians. All right, so now let's discuss arc length and circumference. So let's talk about, for this circle that we had earlier, this time we got a radius of 3. we want to calculate the circumference. If I were to travel all the way around the circle on the surface, what would that distance turn out? So the circumference is 2 pi times the radius, which is, in this case, the radius is 3. We can see that in the problem here. So we know that the circumference is 2 pi times 3, or 6 pi. Replacing pi with about 3.14, we get the circumference. Now, a full circle is 360, or 2 pi. So the arc length has to be smaller than this, right? It has to be a fraction of that. So the arc length for half of a circle, it makes sense that if I were to travel half of the Earth, half of the distance of the Earth, then that's going to be half of that number, right? So the arc length for half of a circle is the fraction for half of the circumference. So if I were to travel, half of the Earth, then that would be half of the circumference of the Earth, right? So how do I do that for any angle? Well, I know that the angle for a full circle is 360. And I know that if I'm traveling half of that, that's going to be 180. So 180 divided by 360 reduces to 1/2. Okay, so that's how we can calculate the arc length, is if we know this angle, we can divide it by 360, convert it to a fraction, and then multiply that by the circumference, and that's going to be the arc length. All right, so similarly, the arc length for any arc of a circle depends on the fraction of the arc measure for the total. All right, so the generic arc length formula, right, in terms of degrees, is the angle that I travel over 360 times the circumference. But we know that the circumference of a circle is 2 pi r. All right, and so this is our formula right here for the arc length. So in this case, we have 95 over 360 times the 6 pi from earlier, and we get 4.97. And so the distance here will be 4.97 to travel from point A to point B. But it would, if I were to travel the whole circle, it would be 18.85. All right, so we talked about arc length and circumference. Remember that a full circle is 360 or 2 pi radians. So in terms of degrees, the arc length formula is given by the angle I traveled divided by 360 for a full circle times the circumference of a circle. In terms of radians, this turns out to be the angle divided by 2 pi, because remember, a circle is 2 pi, and then times the circumference of a circle, which is 2 pi r. Notice that the 2's cancel and the pi's cancel because they're the same on top and bottom. So we're left with just theta r. So in terms of radians, the formula is theta r for the arc length. All right, so find the arc length of arc AD. So we're going from A to D here in degrees and radians. Okay, so if they wanted you to find the arc length this way, they would probably have labeled it as ABD. So that way you knew that, oh, okay, I'm talking about this side. Or they'll say minor arc versus major arc. But here they said AD, so specifically from here to here. So let's do that in degrees and radians. Well, first off, we need to figure out what this angle is, right? And that will help us calculate the arc length. So in order to find that angle, well, we know that this is 43 degrees, 73, and 104. We know that a full circle is 360. So we're going to do we're going to say that the measure of arc AD, not the length, the measure, which is the measure of the angle, all right, is equal to 360 minus, and then we're going to subtract all these other angles, 104, 73, and 43. So go ahead and calculate that real quick. And we get 140 degrees. Okay, so now we know what this angle is. This angle is 140 degrees. All right, so since we know that angle, now we're going to calculate, and we know the radius is 4, so we can calculate the arc length. So let's call this S for arc length. So S is equal to the angle 140, which is a fraction of a full circle, which is 360, times the circumference of the circle, which is 2 pi r, right? So 2 pi times the radius, which is 4. This is the radius here. All right, so we'll go ahead and calculate that. This is going to be 8 pi So we'll do 8 times 3.14, and then we'll do 140 divided by 360. And we get about 9.77. And that's the length of that. And that's in units, since we don't have the units here. So 9.77 units. All right, so that's the arc length for AD. That's in terms of they said the length here, not the measure. So this doesn't really make sense. It's not going to be in degrees and radians. But they let's just say that, for example, that they want us to do the length and the measure. Okay, so we'll do the length and the measure. So this is the measure, and then this is the length. All right, and then we'll convert the measure to radians so that we can practice. So the measure of a arc AD, we'll convert that to radians. So we're going to multiply by pi divided by 180, so the degrees cancel, leaving us with 140 pi over 180. Then we can reduce that. We can divide them both by 20. We get 7 pi over 9. And that's going to be in radians. Okay, so we got the measure in degrees and radians, and then we got the length. So that way we can practice all of them. But if they, in this case, if they want length, they want S. Okay, a sector of a circle is the region bounded by 2 radii and the intercepted arc. So we have, so the sector is shaded here for you. So let's go ahead and calculate, or let's go ahead. So when we look at a sector, we generally want to find one of two things. We generally want to find, the area of that sector, right? And in order to find and we also can find another part of the sector called a segment. So here we're looking at the area. Now remember that the area of a circle is given by pi r squared. You might remember that from a previous class, all right, from another class. So the sector is going to be a fraction of that area. So for example, the area of the circle with the radius of 10 is going to be pi times 10 centimeters squared. 10 squared is 100, so leaving you with 100 pi centimeters squared. Remember that pi is about 3.14, so this is about 314.16 centimeters squared. Now the area of a sector is the fraction of the area of the entire circle. So the area of the sector is going to be smaller than that. So if we calculate that, how do we calculate that? Well, we know it's a fraction of the circle, and we know that a full circle is 360, right? So this is going to be a fraction of that circle. So it's the angle that I traverse around the circle divided by the whole circle area, the whole circle angle measure, times the area of a circle, which is pi r squared. So to calculate this in radians, we instead of 360, we use 2 pi, because there's 2 pi radians in a full circle. And then the area of a circle is pi r squared, so the pi's cancel, leaving us with 1/2 theta r squared. So we got our two formulas here. All right, so in this example, we have it in degrees, so let's use the degree formula. 78 degrees out of total of 360 degrees times pi times 10 squared. That turns out to be about 68.07 squared, which, as we said, is a fraction of that. It's actually smaller than that, which makes sense. All right, let's look at the area of the given sectors. So the sector that is shaded here, we know that the central angle is 165, which means that this arc measure is also 165. We know the radius is 3, so let's go ahead and calculate the area. So the area is a fraction of 360, which is 165 degrees over 360, times the area of a circle. The area of the circle is pi r squared. R is 3, so we got 3 squared. So it's basically 9 pi times that, and that's the area of that sector. Using 3.14 for pi, we get about 12.95 for the area. All right, so looking at the area of this sector here, this sector given in yellow, it's given in radians. This angle is given in radians. So we're going to convert that. We're not going to convert that. We're going to leave it in terms of radians and use the area formula in terms of radians. So that remember that the area formula is the angle, and out of a total of 2 pi radians times, and then the radius is 10. So it's going to be pi times r squared, pi times 10 squared. And then remember that the pi's here cancel, which makes it easier. So you got 1/4 divided by 2. 1/4 divided by 2 is 1/8. So you could do this on the calculator, but I'm going to just kind of show you here. Times 100 pi, that's 100. So we got 100 divided by 8 times pi. You get about 39.25. So we can see that the area of this is a lot bigger than this one, even though it doesn't look like it because it's not drawn to scale. And that's because the radius is 10, so technically the circle in part B is much bigger than the circle in part A, even though it doesn't look like it, just because of the scaling is not, it's not to scale the images. All right, so the areas of segments. So now we're looking at a segment of a circle. Now the sector is, this entire area is the sector, right? So that whole thing is the sector given in red. However, the segment is this portion of the sector. Okay, so that's referred to as the segment. So it's the part of the circle bounded by the arc. This is the arc here, and the segment joining the endpoints. This is the segment joining the endpoints. Okay, so that area in between those is the segment. The area of the segment is found by subtracting the area by taking the area of the sector, which is this whole thing, right, minus the area of this triangle, and that gives us this small green area. All right, so take the area of the triangle, subtract it from the area of the sector, and this is the formula for the area of the segment, which kind of makes sense. Take the whole area minus this little blue area, and that gives you the green area. So remember that the area of a triangle is 1/2 times base times height. The area of a sector we did earlier. So let's look at the triangle and given in blue. We know that it's 60 degrees here. If we cut it in half, well, we know that this turns into a 30-degree angle, right? So now this is going to be a 30-degree angle. And so it becomes a 30, 60, 90 triangle. Remember that in a 30, 60, 90 triangle, the sides are given by x, for the 60-degree side, the shorter side, x squared root of 3 and 2x. So that's the dimensions, those are the sides for a 30, 60, 90 triangle. So that means that the height h is equal to, in this case, x is 4 in this case. So we got x equals 4. So the height is 4 square root of 3. And in this case, the hypotenuse is 8, which that makes sense there, 2 times 4. So the height is 4 square root of 3, and the base is 4. And we know it's 4 because it's always going to be half of the hypotenuse. And we know that the radius is the hypotenuse here, right? So that's how we knew that that was 4, is because it's always half of the hypotenuse. All right, so the base is 4, or the base is 4 for this. And the height is 4 square root of 3. So remember that, and I didn't write this correctly here per se, the entire base of this triangle is actually 8, not 4, because it's 4 times 2. So this should actually be 8 for the base of the entire triangle. So this is going to be 1/2 base, which is 8, times height, which is 4 square root of 3. And that probably will change the number a little bit, so sorry about that little typo there. And in the area of the sector is given by the fraction of the circle, which is 60 degrees over 360 for a full circle, times pi r squared, the radius being 8. All right, so we'll go ahead and we'll figure out the correct measure here. So it's about 5.81 centimeters squared, approximately. It's a rough estimate. So it's a lot smaller than I calculated initially. And so what we do is we do it for a half of that triangle, right? Which, because it's a right triangle, we can use trigonometry. And then we can double the base for the full triangle. All right, so let's look at some more examples so you can give you an idea of how it's done. Not all triangles will be special right triangles, so we just got to keep that in mind. Part A will be a special right triangle. Part B will not be a special right triangle. So we'll show you how to do it for both. First off, let's calculate the area of the sector. Now the area of the sector is given by the angle here, which is 90 degrees, over the total of 360 times the pi r squared, which is pi times 10 squared. All right, so that's the area of the sector. And this is just a quarter of a circle. If you think about it, this is literally just a quarter of a circle, which makes sense. 90 over 360, that's a quarter. So we got a quarter of 100 pi, essentially, is 78, approximately 78 point, let me double check that. So approximately 78.5 is the area of the sector. Now we'll do the area of the triangle next. So the area of the triangle is 1/2 base times height. We'll draw this triangle out. I'm going to draw it with Q on the top. So we know that this is 90 degrees here. Let me draw a little bit bigger here. And actually I'll draw it out more like this. So that way you can kind of see that this is Q, which is the right angle, this is M, and this is N. So because this is a 90-degree angle, we know that, and because these are the same length, because it's the radius is 10, then this is a 45, 45, 90 triangle. And you may recall that in a 45, 45, 90 triangle, this is back in chapter 8, that the side lengths are x, x, and x square root of 2 for the hypotenuse. So if this is 10, 10, then this is 10 square root of 2. And so 10 square root of 2 is our base, okay? So we want the area of this triangle, so which is 1/2 base times height. So you can really use 10 as your base as well here. So area of triangle is 1/2 base times height. But it's not like you needed to find this per se. You only need the base times height, which is, in this case, the base is 10, the height is 10. So this one was actually a pretty easy problem. You only need those two dimensions. So we got the area of the triangle is 1/2 times base times height. 10 times 10 is 100, divided by 2 is 50. So then subtract those two areas. The area of the segment is 78.5 minus 50, which is 28.5. All right, so we're going to go ahead and erase all of this for the next problem. Okay, so for the next problem, we'll do the area of the sector. So the entire sector, we'll do it over here. So we got the area of the sector is the angle. Now we know that this is 144, so that means this is 144. So it's 144 over 360 times pi r squared, pi times 5 squared, the radius being 5 here. And that gives us approximately 31.4. All right, so now that we got the sector, let's find the area of this triangle. So we'll draw this triangle out so we can see it. I'm going to draw it like this. So the radius is 5 on each side. All right, this is T, this is A, this is B. So this is that triangle there. So we need to figure out the height of that triangle, the perpendicular height, right? So we need to figure out the height, and we know, and then the base is this whole thing. This whole thing is the base. So we'll call this X, and then X is going to be half of the total length, B, okay? So this is going to be a 90-degree triangle. This is a right triangle. So for this right triangle, we're going to use trigonometry here. We know that this angle is 144. So therefore, this angle has to be half of 144, which is 72. This has to be a 72-90 triangle, okay? So look, using our trigonometry, we know that sine is going to be opposite over hypotenuse. So the sine of 72 degrees is opposite, which is x, over hypotenuse, which is 5. Again, using SOHCAHTOA. And this is back in chapter 8. If you need to review that, I would review that video for chapter 8 when we did trigonometry. So, and then if I solve for x, I need to multiply by 5 on both sides to get rid of this. So we know what x is. X is 5 times sine of 72. Let's go ahead and calculate that. So we have a bunch of decimals here. So we get about 4.76 for x. So we know what x is. This is 4.76. So that means b has to be double 4.76, so we'll double that. And we get, let's close that. So it's going to be 9.52. So this is B, 9.52. And then the height, so we need to figure out the height. So the height is going to be given by adjacent. H is adjacent to 72, so it's going to be adjacent over hypotenuse, which is the cosine. So the cosine of 72 is adjacent over hypotenuse. So we'll multiply by 5, and that'll give us the height. So the height is 5 cosine 72, which is approximately 1.55. All right, so we know the height, we know the base. We can go ahead and calculate the area of this triangle. I'm going to erase this triangle now, and we'll calculate the area of the triangle. So the area of the triangle is 1/2 times the base times the height, which is approximately 7.378, and then we'll go ahead and find the area of the segment by subtracting those two areas, 31.4 minus 7.378, and get the approximately, and we'll round that to the nearest tenth at the very end. Rounding it to the nearest tenth, that's about 24.0. All right, and so that's the area of that segment. Notice that the area of the segment is pretty large, and that's because we got a really small triangle. The area of the triangle is very small, so notice that it's only 7, and the area of the sector is 31, so the segment is pretty large. Whereas before, the area of the sector was large, but the area of the triangle was also large, which means that the area of the segment was relatively small. All right, that's going to do it for the video, guys. I hope you found this useful. I hope you took a few things, and as usual, I'll see you in the next one.